So we are going to be looking at complex numbers today. Hopefully you can hear me, see me, and well, see the screen at least. And yeah, let's get started. So a complex number is essentially a property where we're taking the surd or the square root of a negative number. Let's say x squared is equal to minus 1. In logic, you can't really take the square root of a negative number and have that become a real output. This means x is not in the real set. However, x squared is indeed in the real set. So, what would the result of this be? Well, we can take the square root, however, the operations that we will be doing is again not in the real numbers. We can say that x is in the complex numbers as x is equal to the square root plus minus the square root, technically, of minus 1. And this we can define as some number I. So we get plus or minus I. So the idea of complex numbers is actually we are looking at the square root of negative numbers. And we can take this definition a bit further. Say for example, we have x squared equal to minus a, for a is positive. Well, in this case, we get a similar case. We get x is equal to the square root of minus a, and assuming that you guys know the properties of surds, we can split this into two different square roots. The square root of a and the square root of minus 1. And furthermore, this can be simplified to give root a I. So that's some pretty simple algebraic terms. And this is in C. Okay? And the link to this is that we will always have a coefficient in front of the I that belongs to the real set. And in definition, we actually know that the real set is a complementary subset to the complex set. So take for example root a. Root a is nothing but equal to root a plus 0i. So there is actually an imaginary term. But the imaginary term of z, let's say, is 0. So we have purely real number. Pretty interesting stuff. And there are quite a few properties that we can use to apply to complex numbers as such. And this can also have applications into calculus. So what's some further examples? Well, let's say for example we have the standard form of a complex number a plus bi. This is just your ordinary form. Well, what would a quadratic look like? Well, let's go ahead and do that. So, a quadratic with the roots a plus bi would look something like this. Okay? And we can actually prove that there's something called a conjugate using this expression. How would we go about doing that? Well,